All right, so we're going to work through. So you should have watched the two calculation videos, or two or three of them that are there yesterday. Making sure you take notes. It's just giving basics on walking through calculations. I'm going to walk through some more calculations today just to make sure we're on the same page. So there's a really good chance you're going to have equilibrium calculations and work you're going to have to do on the AP exam. So that's why we're going to spend a couple days going over it. There's no quiz this week just because there's a couple more notes we have to learn. We'll sum up everything next week, work on practice problems, and take a quiz next week over equilibrium. So this is just more practice. It's going to be me explaining how to answer both of these questions, but I'm also going to highlight very important points and things that we need to make sure we consider when doing equilibrium calculations. So starting with this first question. So looking here, so we're writing the equilibrium constant expression. So that's part A. So remember, when we write that expression, all we're doing is doing products over reactants. So we'll look at our products. So the first product here is HI. So concentration of your products, and I'm squaring it because there's a 2 coefficient. So concentration of your products raised to a power, that power is the coefficient, divided by the concentration of my reactants. Now, both to the 1 power because those are 1 coefficients, and I include all 3 of those because they're all gases. So if you remember, we only include gases and aqueous. Solids and liquids you do not write in the expressions. And so here we got that. Now they're asking us here to calculate Kc. Now when we do this, this is an equilibrium constant expression. So when the numbers that you plug into here, so we're going to take our expression Kc, and all we're going to do is plug in values. So that's all we're going to do. And once we can plug in those values, then we can find the value of Kc. The key to answering this question is you have to plug in values here at equilibrium. So those are the values that are going in those slots. You can't plug in these values here because these are the values that we're starting with initially. And so when you're given equilibrium, so we know this is equilibrium because of double-sided arrow, when you're given those, we're going to make an ICE table. These are very similar to BCA tables before change after that we did with stoic, except now we're going to do ICE tables with equilibrium. So you're going to have your balanced chemical reaction. And you have your ICE table, initial, change, equilibrium. What do you have when you start? How much is it changing by? How much do you have left at equilibrium? So when we look here, we know the closed system contains this much H2 and this much I2. So you can go ahead and plug those in. And it's allowed to reach equilibrium. Analysis of the equilibrium mixture shows, so we know that this is the concentration of HI at equilibrium. So another key is this number goes here because that is the concentration, let me move that over, that is the concentration we have at equilibrium. Let's change that lighting. Maybe that's a little better. Nope, not really. So we still have stuff to fill in our table. So how much of our product do we have before the reaction? Well, because we're given no information, we can assume it's 0. And so we got to fill this in. And so 0, we know we lose reactant to gain product. So subtract and add. And here we know that if we were to fill this in, what 0 plus what equals 1.87 times 10 to the negative 3? Well, we know that that would be 1.87 times 10 to the negative 3. So that's how we can fill that part in there, because we have to be able to complete this, because again, we want these equilibrium values. Now, this is the change right here if you have 2 moles. So what is the change if we have 1 mole? And if you remember with BCA tables, we would plug in minus x, and then this right here would be plus 2x. Now, you could still do that. And so you could say 0 plus 2x equals 1.87 times 10 negative 3, and you could then solve for x. And you could get that that's 9.35 times 10 negative 4. And now you know what to plug in right here. You know that this is 9.35 times 10 negative 4. So you can go ahead and still use x the same way we did with BCA tables. And all you have to do is you can just do this minus this will equal number, this minus this will equal number. So you can go ahead and figure out what that is. And so now that we have all 3 of those values at equilibrium, all we have to do is plug them in to that equation right there, and we then solve for the K constant. And so HI is 1.87 times 10 negative 3. Concentration of H2, let me erase this just so I can get a little more space. So we'll go 6.5 times 10 negative 5, and then we'll put 0.001065, and we can solve for our K constant. And I'll kind of just break that up just so we don't confuse that. And so 1.87, I use E just so I can keep order of operations correct. And I'm getting 50.5 as the K value. So we write our expression. The key here, when you do equilibrium problems, we know it's equilibrium because of double-sided arrow. We got to make our ICE table. And again, a common mistake that kids will first make when they solve this is they just plug in those 3 numbers they get there into this expression, and then they solve for K. That's not right, because these are initial values. I don't plug in initial. When you have an equilibrium constant, you have to plug in values at equilibrium if you want to solve for that value. And so is it reactants favored or products favored? Remember, so I would say this is a lot greater than 1. So key here, justifying our answer. So I would say products favored because K is a lot greater than 1. And that's our justification. If K was a small number, a lot less than 1, it would then be reactants favored. All right, so if you haven't done number 2, maybe pause the video, try to answer number 2 on your own. And I would encourage you just see how far you can get. And then you can come back and then watch the video and see if you did it correctly. So the equilibrium constant, For the decomposition of PCl5 into PCl3 and Cl2, what are the equilibrium concentrations? So this question is a little different. So in this first question, we solved for the K value. This question, they give us the K value and they're wanting us to use that to solve for equilibrium values. So the first thing, because we know this is at equilibrium, we're gonna write the reaction. So PCl5 is decomposing, remember decomposition reactions, they're breaking down into PCl3 and Cl2. We'll go ahead and put gases there. Remember, state of matter is important. Gases we include in it, solids and liquids we do not. So looking here, for me, I know it's equilibrium. I want to make my ice table. I'm also going to write my expression. Let me kind of move this up a little bit. So when we look at solving this, what are the equilibrium concentrations of PCl5, PCl3, and Cl2? So essentially what we're trying to find is what are the values that are going to go in our table right there? What are those values? So let's look at this table and figure out everything that we know. Well, we know that our equilibrium constant expression, or our equilibrium constant is 0.0211. We know that. And then we know the initial concentration of PCl5 is 1. So we know I start with 1. If you remember from, and I should have mentioned this earlier, but if you remember from BCA tables, the only numbers that we can put in this ice table is moles, or the BCA table is moles. In equilibrium, I can put moles or I can put concentration, which is molarity right there. So just make note of that. We can put molarities in the table just like we did here up top right there. Concentration values, molarity values are okay in the table for ice tables. So we're looking here, 0 and 0. We're not given any information about those, so we assume we start with none of it. And so then this goes back to, so how do we fill this in? We can fill this in. It goes back to if I don't know the change. So we need to first make sure that this is balanced. So 1p, 5 chlorine, 3 and 2 is 5. So we're balanced. So it's 1 to 1 mole ratio. So then this would just be minus X. This would just be plus X. This would just be plus X. And so we can fill this in as X, this in as X, and this is 1.00 minus X. Excuse me. Now we can also write our expression. So we've got to find some way to solve for X, because once I solve for X, I know those concentrations. And so we know the expression is concentration of Cl2 times the concentration of PCl3 divided by the concentration of PCl5. That's our expression, right? They're all raised to the 1 power because the coefficient is 1. They're all included in the expression because they're all gases. Remember, gases and aqueous are the only two things we include. And now I know, so we know that this equals 0.0211. So we can take these and plug them in. So and this is the key step here. So if I plug them in, I can say Kc equals X times X divided by 1.00 minus X, right? Now, if you look, we can say 0.0211 equals X squared divided by 1.00 minus X. Now, one thing to make note of here. You can solve this set equal to 0. You can use the quadratic formula, but we are not going to do that. So this is the trick. This is what we need to know. So this X right here, and only this X, that X is negligible when K is a lot less than 1. And what does that mean? That means that when your K value, and so this is a lot less than 1. When this K value is really, really small, what does that mean? A really, really small K value means reactants favored. What that means is your reactants are not going to be changing by a lot. So in reality, this X becomes negligible, meaning we don't need it. And so here, I wouldn't write it. I would just say that this is just 1. Is it going to change? It'll change slightly. Can you use a quadratic formula? You can if you want, but I would say don't do it. Save yourself the time. That's just going to be 1. Because this is a small K value, it's reactants favored, meaning at equilibrium, you have more of the reactants present. And so this is negligible. This is true. When K is a lot less than 1, you can assume this X is negligible. And the hint here, for our reactants, this change is always going to be negligible because when we need to assume it, they're going to give you a small K value. And so then that would change this here. And so now all you have to do is solve for X. So you can just multiply this up. So we're getting let me move it over here just so we can see it. We're getting 0.0211. So I'm just coming up to here. 0.0211 equals X squared. Square root both sides. And we get that 0.145 equals X. So now you know the equilibrium concentration values, right? This is 0.145, this is 0.145, and that would then be 1. So if we're looking back to the question, what are the equilibrium concentrations of each of those? So if we want to, make sure we're answering the question, I would say concentration of PCl5 equals 1. Concentration of PCl3 equals 0.145. Concentration of Cl2 equals 0.145. And so those are the 3 values. Again, that's what we're getting here from the table when we solve that X was 0.145. So this is just these are the 2 main scenarios you could see when solving for these equilibrium questions. Here, you could write you're gonna have to be able to write the expression, if you calculate the value, we're just plugging in whatever these values are here. We need an ICE table to solve those values. Coming down here, they give you the K value, and then we use that K value to figure out what the values at equilibrium are, and we got those right there. Again, if you have any questions, join the online office hours later.